Okay, class. So for this video, what we're going to discuss is chapter 6, which is current mirrors, current source, PNP transistors, and transistor switching network. So for this chapter, we're going to step back a little bit because all of what we're going to discuss in this part are all DC. Kumbaga, so hindi tayo mag-AC analysis dito. Also, sa transistor switching na part, instead of focusing on amplification, ang titingnan natin ngayon dito is how does a transistor works as a switch ba. So start tayo with the current mirror muna. So yung current mirror natin, this is a DC network in which the current through the load is controlled by a current at another point in the network. So this is the current mirror circuit natin. So it is composed of, nakita natin, dalawang transistor, and the assumption is, or the requirement is that this Q1 and Q2 ay parehas sila ng value. Tas parehas sila ng specifications, parehas sila ng characteristic. Tapos, makita natin, we have I control and a current IL dito. So, ang gusto nating mangyari is that the current at your load is i-mirror niya yung control current mo. So, this control current, ikaw yung nagsiset nito. And kapag naset mo na siya, ang gusto mo mangyari is itong load natin, ang dumaloy sa kanya is the current equal to your I control or your control current. So itong load na to, dito mo sinasaksak or pina-plug in kung ano man yung device or circuit na gusto mo magkaroon ng constant current. So let's say for example, meron kang isang circuit na kailangan ma-feed mo siya ng 5 milliamperes na constant current. So, pwede mong dito siya isaksak sa part na ito nung circuit mo. Siyempre, isasaksak mo siya ng naka-series kasi current yung papapasukin natin. So, this is the general circuit of a current mirror. But we have different variations. I-discuss natin mamaya. Now, what I want you to notice is the different currents and mga voltages na nagpo-flow dun sa circuit natin. So, we have a voltage source that is VCC. And then we have a variable resistor right here. Kasi yan yung gagamitin mo to control the I control. And then we have two transistors. And yung collector ng Q1 natin is connected to their bases, to the bases of Q1 and Q2. Now, since these are the same na transistors, so kung same siya ng characteristic, then ibig sabihin, kapag naka-forward biased yan, same sila ng base to emitter voltage or similar sila ng forward voltage natin. Kung parehas sila ng forward voltage, then parehas din yung mga currents nila. That is IB1 and IB2, that is also equal dapat kasi parehas sila ng VBE tsaka ng VBE1 tsaka VBE2 natin is parehas. Also, makita natin the current from the collector flowing to the bases, pinangalan natin siya as IB. That's the total current and that is equal to IB1 plus IB2. So yan, babalikan naman natin yung mga yan later on. Now, we have an approximate value for VBE that is 0.7 volts. So assuming they are identical, VBE is equal to VBE1 is equal to VBE2 rather, and IB1 is equal to IB2. So on this side class, this figure is the characteristic curve of a transistor. This relates yung VBE natin tsaka IB. So sinabi ko kanina, the 0.7 is just an approximate. Diba ganun din naman tayo sa diode? This is the characteristic curve nung base to emitter junction natin sa isang transistor, which is very similar to a simple diode na PN junction lang. So, kinompare natin yung VBE tsaka yung IB natin. So kung ganun class yung case, mapapansin natin that yung VBE natin, hindi naman talaga exact yung value, di ba? As discussed in our previous chapters or previous lessons nung nag-LX1 tayo tungkol sa diode. Yung totoong value niyan, this is just approximately 0.7 volts. And we assume na kapag tumaas pa doon yung voltage mo is 7.7 volts lang yung natin, yung ating output. However, di ba meron tayong tinatawag na internal resistance, and yung internal resistance na yon nagko-contribute yon sa total na VBE natin. Kasi the more resistance na nagkakaroon, pag may internal resistance yan, pag tumataas yung IB natin, then ibig sabihin, tataas din yung voltage. Kasi, di ba, current is directly proportional. So, ganun yung nangyayari. However, in most cases, nag-approximate tayo. But in reality, ganito talaga yung itsura niya. So, assuming ito yung 0.7 mo, and then ito yung value ng IB1 mo, pero pag tumaas yung IB1, tumataas pa talaga tayo kesa sa 0.7. Ayun. So, kung ganito pala at similar yung Q1 natin sa Q2 natin, then kung merong kuryente na dumadaan doon sa kung merong voltage drop rather doon sa mga transistors natin, kapag parehas sila ng value, then dapat parehas din sila ng input current. So, kung parehas yung VBE mo dito, tsaka VBE sa kabila, your voltage drop sa Q1 is equal to the voltage drop at Q2, at similar silang transistor, then your IB and IB2 is similar. Kasi kumbaga, isa lang yung characteristic curve nila. So, kung may VBE 1 ka, equal yun sa VBE 2, then yung IB1 mo is also equal to IB1. So, that is the assumption. So, yan. So, try nating i-derive paano nga ba nakakapag-provide siya ng constant na current or na-mirror yung current ng I-control natin dun sa load natin. So, from the figure, it's easy to identify na yung IB natin is equal to IB1 plus IB2. That's just Kirchhoff's current law. And if IB1 is equal to IB2, then ibig sabihin, yung IB natin is just twice ng IB1 or twice ng IB2. In addition, yung I-control natin, from the circuit din ito, I-control natin, that is equal to IC1 plus IB. Diba? Kirchhoff's current law din. Now, alam natin that IB is already equal to 2IB1, so sinubstitute natin siya dito. So we have I-control natin is equal to IC1 plus 2IB1. Next, alam natin ang relationship ng IC and IB. So IC1, that is equal to beta 1, IB1. Then, substitute natin yun doon. So we will have I-control is equal to beta 1, IB1 plus 2IB1. Or factor out natin yung IB1, we will have beta 1 plus 2 IB1. Now, assuming that, or since it's typical na values ng beta, mataas kaysa sa 2, pwede na nating tanggalin yung plus 2 dito. Pag tinanggal natin yan, then approximately, we will have I control ay equal sa beta 1 times IB1. So which is similar to the value of IC. So ang assumption natin, class, is that this IB na nahati sa IB1 at IB2 is negligible na yung value or sobrang mababa yung value niya. And your I control is also equal to IC1, which is equal to beta 1 IB1. So ang IB1 natin is I control over beta 1. So that is our IB. So if the control current is raised, this one, the resulting IB1 will increase. So, nakuha nyo ba? So, paano natin ba kukontrolin yung value nung I-control? So, let's say for example, binabaan mo yung resistance nito. So, pwedeng tumaas yung kuryente natin. Now, kapag tumaas yung current natin, your IB1 will also increase as this equation is telling us. Kapag tinaasa mo yung IB1, then pag tinaasa mo yung I-control, rather, tataas din yung IB1 natin. If IB1 increases, the voltage VBE1 must also increase. So, balikan natin to. So, kung tumaas daw yung IB1 natin, so halimbawa, ito yung normal na value ng IB1 mo, tataas siya, let's say at this point. So, kapag tumaas yung IB1 natin, tataas din yung value ng ng voltage natin. Let's say tumaas yung IB1 mo from this point, napunta siya sa point na to. Pag napunta siya sa point na yan, yung voltage mo, yung VBE1 mo will also increase. So, yun yung ibig sabihin natin doon. Ayun. And if VBE1 increases, then VBE2 must also increase by the same amount ng IB. Bakit? Kasi nga, they are identical. So kung identical sila, tumaas yung voltage nito, then syempre tataas din yung voltage nito, nakaparallel yan dalawang yan. So magkakaroon yun ng pag-increase. Hindi, kumbaga tumaas yung IB1 mo, tumaas yung IB2 mo. So syempre parehas tataas yung VBE mo dito sa mga junction na to. So ganun class yung mangyayari. So kung ganun yung case, tumaas yung IB mo, then your IL from the figure, makikita natin that IL is the current equal to IC2. Tama? Mali pala ako nang napili. Pag titingnan natin tong figure natin, IL is equal to the collector current of the second transistor. And yung collector current natin dito, that is equal to beta 2 IB2, which is equal to IL. So therefore, kung tumaas yung IB2 natin, nag-start tayo with the increase of I control, di ba? Tinasa natin yung I control, tumaas yung IB, tumaas yung VBE, tumaas yung ito pala. Nagsimula tayo with increasing I control, tumaas yung IB because of that. Tapos tumaas din yung IB1 because of that, tumaas yung VBE1 because of that, and syempre, may tataas din yung VBE2 natin, and itataas din niya yung IB2 natin with the same amount ng in-increase dito sa kabila. So kung in-increase natin yung IB2, then syempre tataas din yung IC2 natin, which is equal to IL. So nakuha na. Ang nangyari, yung IL mo na nagpo-flow dito is equal dito sa current mo na to. Pag tinaasan mo yung current at I control, tataas din yung current mo dito sa side na to. So therefore, mini-mirror nung current at this side, yung current na ginagawa mo or pinapresent mo dito. So that is how the current mirror works. So referring to the figure, we find that the control current is determined by, mag-aano lang tayo dito, maglo-loop. So yung loop natin dito is from VCC, I control, tapos kahit alin dito sa dalawa, pwedeng sa Q1 or sa Q2 ka dumaan kasi parehas naman ang value yan. And ang assumption natin that's 0.7. So let's say dito tayo dumaan. So yung equation natin dyan for the KVL is VCC plus I control, mali pala, minus to, minus I control times RR minus VBE, hindi ko pala nalagay yan, plus minus VBE is equal to 0. Pag in-extract natin yung I control, we will arrive at this equation. So that is how we determine. So kung ang VCC mo is to change I control, ang pwede mong gawin is baguhin yung VCC or baguhin yung R. So in this case, nakita natin 10 volts yung VCC, so constant yan. But what we have here is a variable resistor. So you can change your I control by changing the value of your resistor. So kung meron kang potentiometer dyan, pwede mong gamitin yon to change. Kasi VBE, hindi naman nababago to basta-basta since this is a characteristic ng isang specific na transistor. So, yun, ganun nangyayari yung pag-mirror natin. And this is how you set your I control. Again, you have two choices how to increase or decrease the value of I control. You can change the value of VCC or you can change the value of the resistance. Now, aside from that, papaano naman kung yung IL naman yung magbago? Kasi kapag nagbago yung I control, alam na natin that your IL will also change. I-mirror niya yung mangyayaring change dun sa I control. And kung ano yung current dito, yun pa rin yung current sa kabila. Now, papaano naman kung yung current sa load yung magbago yung value? So, let us assume na tumaas yung IL natin. What will happen if your IL increases? Now, this network, it also has a built-in control that will try to ensure that any variation in the load current will be corrected by the configuration itself. So kapag daw tumaas tong IL, meron siyang mechanism or merong capability itong circuit natin na ipagparehas yung value or ibalik rather. Kasi syempre, ang worry natin, ang mini-mirror natin is eye control. 'Di ba? So kanina, pag nagbago yung eye control, gusto natin magbago yung IL. Pero this time around, yung IL ang magbabago. Pag nagbago ba yung IL natin, gusto nating magbago yung eye control? Hindi. Kasi kaya ka nga nag-set ng control current para yun yung i-mirror nitong circuit po na nung current na pinapasok mo sa load natin. So dapat, kahit tumaas yung current natin, ang gagawin nung circuit is ibalik niya sa normal na level yung IL natin. So dapat, hindi to pwedeng tumaas. Kasi pag tumaas yan, hindi niya na mini-mirror to. O hindi naman pwede na dahil tumaas to, tataas din to, di ba? Kasi hindi na yun yung control current na sinet mo. So paano siya nag-work? So the entire sequence of events, eto siya. So let's say for example, tumaas yung value ng IL natin. So kung tataas ang value ng IL, tataas din ang value ng IC2. Bakit? Kasi IL is equal to IC2. And yung IC2 natin, pag tumaas, tataas din yung IB because they are directly proportional to each other. Beta natin is constant. So, kung beta natin is constant, pag tumaas ang IC2, then dapat tumaas din yung IB2 natin. And kapag tumaas yung IB2 natin, based from your characteristic curve, kung tumaas yung IB2, let's say, ito na yung bagong value ng IB2 mo. So, tataas din yung, VBE2 pala. Halimbawa, tumaas yung VBE2, magbabago rin yung value ng IB2 mo. So, tataas din siya. So, therefore, pag tumaas ang IB2, tataas ang VBE2. Now, kapag tumaas ang VBE2, which is this part, ng circuit natin, mapapansin natin, connected directly yung base ni Q2 sa collector ni VC1. So therefore, masasabi mo that this portion of the circuit is parallel to VBE2. Tama? So kung parallel siya at tumaas yung value nito, then tataas din yung voltage at this point. And yung voltage from this point, papunta sa ground, that is your VCE. Diba? Kasi yung voltage mo from this point papunta dito, that is just equal to your voltage from this point papunta sa ground. So, tataas din yung value ng VCE1 mo. And kapag tumaas yung value ng VCE1, bababa yung current mo. Bakit bababa? Kasi ibig sabihin nito, mas marami yung kinain na voltage nitong portion na to ng circuit. And kung ganun yung case, mas mataas yung voltage at that point, bababa yung voltage mo at R. And since constant yung R, pag bumaba ang voltage mo dito, bababa rin yung current mo na nagfo-flow dun sa R, which is yun yung IR natin. And that IR, that's actually your control current as well. Now, kapag bumaba yung IR mo, yung current mo dito is bumaba, then sabihin, pati ito, mababa. Bababa na rin yung IB mo. So, kapag bumaba yung IB mo, bababa rin yung IB2, tsaka yung IB1. And kapag bumaba yung IB2, nabanggit na natin kanina, related siya sa IC2, bababa rin yung IC2 natin. And kapag bumaba ang IC2, similar lang din naman yan kasi sa IL, so bababa rin yung IL natin. So therefore, pag tumaas yung current, automatic, ibababa niya ulit. So yun yung sinasabi natin na built-in control na ini-ensure niya na kapag nag-vary yung load current mo, ay ibabalik niya sa normal na value. Kasi kung tumaas siya sa umpisa, at the end, because of the circuit configuration, ibababa niyo ulit to the same level ng eye control natin. So, ganun class yung papaano niya na-maintain yung current kahit na mag-change to. And all throughout our discussion, napansin na ang IL yung nag-a-adjust. Never na si eye control yung nag-adjust for the value of IL. Kapag nag-change yung eye control, magbabago yung value ng IL. Kapag nagbago yung value ng IL, hindi may magbabago yung change ng eye control. Sa halip, nung circuit configuration natin, ibabalik niya yung value ng IL to eye control. So that is how a current mirror works. So example, find the mirrored current I in the circuit. So nagbigay na tayo ng formula kanina, di ba? But then again, as long as, di ba, katulad naman ng sinasabi ko lagi, kung tayo ay familiar with KVL or sanay tayo mag-loop ng circuit, hindi na natin kailangan magkabisa ng formula. So gawin lang natin, loop tayo dito, mula 12 volts papunta sa 1 0.1 kilo ohms papunta dito, then papunta sa ground. So ito yung direction ng current. So ito yung sign natin. So kapag ganyan, maglulup lang tayo, we will have 12 volts minus 1.1 kilo ohms times IC, or which is also your I control, is equal, minus ulit VBE is equal to 0. Which, yan din naman yung formula natin kanina. So, yung solution natin is yung I control natin, or to be specific pala, di ko na paliwanag. Ang hinahanap is I, and this is the current I. But this is a current mirror circuit. So therefore, this current na I na to is also the current flowing here, which is your I control. And we can easily solve for the current at this side of the circuit. So, ang answer natin is 10.27 milliamperes. Another one, calculate the current I through each of the transistors Q2 and Q3. O ano kaya yung effect dito sa circuit natin na to? So, actually, parehas lang. Kasi ang hinahanap is I control. Kung mapapansin natin, tama na nakaparallel silang dalawa sa isa't isa. But then, if these are similar transistors, hindi naman mag-iiba yung computation natin masyado. So, ang gagawin lang natin dito, loop lang din tayo. Hanapin natin muna yung I control natin. And then later on, tingnan natin kung paano yung magiging effect niya dun sa circuit. So since VBE1 is equal to VBE2 is equal to VBE3, then IB1 is equal to IB2 is equal to IB3. So this is still based from the characteristic curve ng transistor natin. Na ang sinasabi na kapag pare-parehas na ng transistor, pare-parehas yan ng VBE, ng value ng base to emitter, at kapag nag-change yung value nila, may kasama siyang change din in the value of IB. So therefore, hindi mangyayari class na baka kasi ang inisip nyo, halimbawa, pag tinignan kasi natin yung flow ng current, kanina kasi, this is your IB. Then may nag-flow na current dito, may nag-flow na current dito. Ang assumption natin kanina is similar yung current na nag-flow sa side na to, and then yung current na nag-flow sa side na to. So, ganun pa rin ba dito? So, hindi ganun. Kasi syempre, if this is your IB1, yung mag-flow na current dito, that is your IB3 plus IB2. So, dito pa lang yung IB3 tsaka IB2. Diyan pa lang sila mag-flow. So, baka kasi mamaya akala nyo, since IB1 to, equal yung IB3 plus IB2 sa IB1. No. Since these are all similar transistors, same sila ng mga input characteristics, same sila ng specifications, so same sila ng magiging VBE. At kung same sila ng mga forward voltage, same din sila ng magiging base currents. So kung ganun yung case, yung I1 mo dito, yung I mo dito, tsaka yung I dito, that is just equal to I control as well. Kasi di ba ang relation naman na pinapakita natin is because they have similar IBs, they have similar currents at this point. So, normal na pagsosolve lang yung gagawin natin. So, in this case, mag-loop tayo ulit from this point, papunta sa base nila, tapos papunta sa ground. So, kung gusto mo na maiba, pwede rin naman dito ka dumaan. O, tapos papunta rin sa ground. Or pwede na dito ka dumaan, papunta sa ground. Kung mapapansin, pare-parehas lang yung magiging equation natin. So, substitute na natin siya. We will have I control is equal to 6 volts minus 0.7 volts over 1.3 kilo ohms. Your I is 4.08 milliamperes. That's your I control, and that is also your I. Ayun. So, similar sila ng value dito. Now, we also have other configurations ng mga current mirror circuit. So, this one, yung nasa left side, this is a current mirror with higher input impedance. And on this side naman, kung napansin, ang gamit natin dito is a FET or an FET, to be specific, a JFET. So, itong circuit na to, yung current na I mo dito, that is also your current na I control. So, paano mo malalaman yung I control? O, maglo-loop ka na lang din. Huwag ka na maggabisa ng formula. Kasi for this one, kung maglo-loop ka from VCC, papunta sa R, papunta sa VBE, then dito tayo, tapos VBE ulit. So kung ganun yung case, yung equation natin dyan will be VCC plus minus, minus I control minus VBE minus VBE is equal to 0. So therefore, ang kakalabasan is I control is equal to VCC minus 2, nakalimutan ko ilagay yung R dito, minus VBE over R. So similar lang nung kanina, except this time around, dalawang beses natin dinamaan yung VBE. So, di ba, mas okay talaga pagka sanay tayo mag-loop kesa nagkakabisa ng formula. Now, for this one naman, similar lang siya, but constant na yung IDSS natin. Di ba, IDSS, that is the drain to source saturation current ng isang JFET. And yung IDSS natin, nakukuha natin yan kapag ang bias natin is 0 volts dun sa VGS or wala tayong bias dun sa VGS. So, ibig sabihin, magfo-flow lang yung current natin maximum. And the maximum value is IDSS. So, ang difference lang nito, instead of yung VCC, yung gagamitin mo, kumbaga itong parameters, di ba, may parameters tayong ginagamit, yung R, tsaka yung VCC para makapag-provide ka ng voltage. Dito, ang gagamitin mo is the parameters of AJFET. So, alam naman natin, di ba, yung formula for IDSS, so yun yung ipoprovide niya na current dito. So, instead of solving via the circuit, you just solve for the value of IDSS na may formula naman tayo. So, yun yung magiging load mo sa current. Ay, current mo sa load pala. Ayun. So, that is it for the current mirrors. So, ginagamit to sa different parts ng circuit, sa mga integrated circuits rather, sa mga differential amplifiers. So, ginagamit natin itong mga current mirrors na to for the purpose nga to provide a value of current na similar to one portion of your circuit. Yan. So, next naman tayo, we have the current source naman. So, current source, a practical current source is a current supply in parallel with a resistance. Now, ang gusto natin, the ideal na resistance natin is infinite. So, kumbaga, open siya. Yun yung ating practical na, yun yung ating desired or ideal na current source. Yung resistance niya is sobrang taas. Bakit gusto natin ng sobrang taas na resistance? So, how do we connect a circuit to our current source? So, kung current source yan, so syempre, i-connect mo siya ng naka-series to this current. So, i-connect mo siya, let's say, dito sa part na to, dito mo i-connect yung circuit mo. Mapapansin natin na may current divider na mangyayari. So, mahati yung current mo, may pupunta dito. Let's say, ito yung IR mo, and then may pupunta dito. Let's say, this is your IL. Ito yung load mo. Now, if you want to provide a constant current, ang gusto mo is walang current na mapunta dito sa IR. So, kung sobrang taas ng value nito, then yung IR mo, sobrang baba ng value. And lahat ng current mo mapupunta sa load mo. So, that is why, ang ideal na current source natin, its resistance is sobrang taas. Infinity dapat. Kasi kung infinity yan, yung if R natin is equal to infinity, then lahat ng current mo will go to the load instead of may mapupunta sa IR. So, ito yung ideal na circuit natin for the current source. However, in reality, meron siyang resistance. Pero sobrang malaki naman siya. So, majority of the current is napupunta pa din doon sa load natin. So, constant current circuits, they can be built using bipolar devices, bipolar junction devices, and FET as well, and combination nilang dalawa. So, BJT muna tayo, bipolar transistor, bipolar junction transistor constant current source. So, ito yung itsura nung circuit natin. So, this kind of circuit, ang output current natin dito is this IC. So nakapag-provide tayo ng current na constant na ang value is IC. So dito natin connect yung load natin. So analyze muna natin papaano ang gagawin muna natin na computation. For this one, may assumption tayo na gagawin. If you will look at this circuit, this is actually a voltage divider circuit. Diba? Sa base natin, may R1 saka may R2. Usually, ang ginagawa natin dito, tine-Thevenins, diba? But may assumption tayo na gagawin. Instead of Thevenizing the circuit, what we will do is just assume a value of voltage at this point. Kasi diba, yung voltage at this point, that is the voltage at your base. Diba, ang usual na ginagawa kasi natin, nagte-Thevenins tayo to solve for IB. Kasi pag na-solve natin yung IB, we can solve for the other currents. But this time around, hindi tayo magsosolve ng IB muna. We have a different way. Ang isolve natin is VB. Kasi kapag na-solve natin yung VB, you can solve for VE. Diba? Kasi yung VBE mo is constant. So may relation ka na agad ng VB tsaka ng VE. So you can solve for VE. And if you can solve for VE, you can solve for IE. And if you have solved for IE, you can solve na for IB, you can solve na for all of the equations na on the circuit. So mag-assume tayo dito. This assumption is allowable kapag yung base current, yung input impedance natin, base input impedance is mas mataas kaysa sa R1 saka sa R2. So if your R in base is much greater than R1, hindi, pakamalito kayo, R1 or R2, then pwede nating i-assume na lang na yung base current mo is ganito. So mag-voltage divider tayo. We will assume that the voltage at this point is equal to the voltage at R1. So ganun class yung magiging assumption natin. So kung ganun yung case, then therefore, using voltage divider rule with an input VEE or input voltage na VEE, so we can have this equation. So voltage divider VB times R1 over R1 plus R2 times negative VEE. And if nakuha natin yung VB, we can solve for VE because VE is equal to VB minus VBE. This is double subscript notation formula. And if masosolve mo yung VE, di ba? Kung masosolve mo yung VE dito, then you can make a loop papunta sa ground, which is papunta sa negative VEE mo. So we will have a formula for IE. So to be exact, yung loop equation natin dyan will be positive to, negative to, tapos ganun din dito. So positive, tapos negative yung lalabasan. So we will have negative VE, tapos minus IE, positive pala to dapat. IE, tapos RE, tapos lalabas ka sa negative. Minus, kung plus, minus, tama. Minus, VEE or simply plus VE kasi kung dun ka lalabas. So equal to 0. So we will have tama ba? Minus din dapat to. Sorry. Okay, ulitin ko itong ano. Ayan, so maglo-loop tayo on that side. Hindi ko nasusundan tong ano. So we will have, kung meron ka dito, na node. So, positive yan. Positive, negative. Tapos, this is negative, positive. Ayan. So, we will have VE na negative minus IE, RE plus VEE. Ayan. Equal to 0 volts. And kapag inayos natin yan, so we will have IE VE plus VEE over RE. So, tama, plus talaga to. Okay, so linawin ko lang Sorry. Kasi di ba ito, node to. So, kung node yan, positive to, negative ka papasok, kumbaga. So, ang nilabasan mo dito, positive VE. Nilabasan mo dito, negative IERE. Ang nilabasan mo dito, positive VE. Sorry, nalito din ako dito kasi. So, ang kakalabasan talaga na equation natin ay magiging positive VE minus IE RE plus VEE is equal to 0 volts. So therefore, ang kakalabasan nating class is kapag minove natin sa isang side yung IE, we will have VE plus VEE over RE. And IE natin, this is approximately equal to IC, given na maliit lang yung IB natin. So therefore, makakapag-provide tayo ng constant na value ng IC dito. So example, calculate the constant current I in the circuit. We are asked for the constant current here. So to get that, we just need to get the value of IE, which nakuha na natin yung equation kanina. So pwede rin na, yun nga, mag-loop na lang tayo or so, gamitin natin yung mga formula. So again, the first step is, instead of Thevenizing the circuit, we just get the value of VB here. That is approximately equal to your voltage at R1. So kunin lang natin yung voltage dito. We can use voltage divider. Ang assumption natin, yung 20 volts na to nahati dito sa dalawang to. So therefore, we will have VB is equal to 5.1 kilo over 5.1 kilo plus 5.1 kilo times negative 20 volts is equal to negative 10 volts. So actually, no-brainer na siya kasi nakita natin 5.1 to 5.1 tapos may voltahe ka. Ibig sabihin, mahati lang siya dun sa dalawa. Next, kunin natin yung VE to get VE minus 0.7 lang. So we will have negative 10.7 volts. That's our VE. Now, loop na tayo sa VE natin or use the formula or the equation that we had or we were able to derive for IE. We will have negative 10.7 volts minus 20 volts over 2 kilo ohms. So that is 9.3 volts over 2 kilo ohms. We will have 4.65 milliamperes as our I. So that is our constant current. So ganun lang siya. Parang it's just really with the characteristics na innate sa mga transistor natin, pwede siya mag-provide ng constant na current. Yeah. Next, another variation ng constant current source natin is one using a Zener diode. So, eto, mas madali na yung computation nito. Alam naman natin kung paano nag-work yung Zener diode, di ba? So, kapag tama yung pagkakabias natin sa kanya, it can serve as a voltage regulator. So, for this one, yung Zener diode will be a factor kung ano yung magiging output current natin. And to solve for the output current, we can simply make a loop na lang dun sa mga known na values natin. For one, VZ, that is, alam natin yan, di ba? Kasi sineset yan eh. Alam mo yung value ng VZ dahil, yun yung mismong value talaga ng Zener diode natin. Sabihin natin, ang value niya is 5 volts, ganyan. So, constant yan. So, magandang gamitin natin siya. So, mag-loop tayo dito. Ayan, tandaan na lang or review na lang kung paano ba natin sinasign yung natin, yung Zener diode. At kung titingnan, ito yung anode, ito yung cathode. So, ibig sabihin, naka-reverse bias siya kasi dito yung anode mo tapos naka-connect sa VEE. So, this is reverse bias. At kapag naka-reverse bias siya, magsaserve siya as a voltage regulator na equal to the reverse saturation voltage niya or reverse bias voltage, which is yun nga yung VZ natin. Pero kapag naka-forward bias yan, as an ordinary diode lang, so parang 0.7 lang din yung voltage drop niya. But this time around, nakita natin, negative to, tapos connect mo sa anode, so naka-reverse bias yan. So ang voltage drop nito is equal to your Zener voltage, not to your barrier voltage or knee voltage. So, loop lang tayo dito. So, pag nag-loop tayo dyan, we will have positive VZ minus VBE plus minus IE RE is equal to 0 volts. So that is our working equation. And kapag inalis natin yung IE or in-extract natin yung IE, we will arrive at IE is equal to VZ minus VBE over RE. And we know that IE is approximately equal to I. So, ganun lang, makukuha na natin yung constant current. Example, calculate the constant current I in the circuit. O, napakadali na nito. Pwedeng wag na rin tayo magtingin ng tingin nung pangalan nito. Wag na natin tingnan yung formula kasi lulup ka lang naman dito. So, we will have 6.2 volts minus VBE, which is 0.7 volts, minus 1.8 K times IE is equal to 0 volts. So, we will have IE is equal to 3.06 ohms and at 3.06 milliamperes. And this 3.6 milliamperes is also equal to your I. So, ito na ngayon yung constant current natin. Ayan. So far, madadali pa. And DC analysis lang talaga yung gagawin natin dito. Ayan. So next naman is PNP transistors. So yung PNP transistors natin, similar lang yung gagawin nating analysis. But kasi kung napansin, pati dun sa mga review sessions natin, what we use ay mostly mga NPN transistor. And this time around, magkakaroon lang tayo ng konting in-depth na discussion about how PNP transistors work naman. So the good news is, parehas lang talaga sila. Ang difference lang natin is the direction of the current. Kasi di ba ang symbol ng NPN is ganito. Yung arrow natin is palabas. Tapos si PNP naman, yung arrow natin is papasok. Now, ano ba yung sinisimbolize ng mga arrow na yan? It symbolizes the direction of the current. Yun lang. But the computation, pare-parehas lang. Ang magiging iba lang sa atin dito, iba yung sign mo. Iba yung, kung magluloop ka, iba yung direction. Kumbaga, nung paglulup mo. So, ganun lang yung mangyayari. And for this part, we will be solving a PNP transistor circuit. Kasi, mas madali siyang maintindihan since may background na tayo kung paano ba mag-solve ng NPN. And ganun din, I would suggest na hindi talaga tayo magkaroon ng or mag-compute using formulas or magkabisa. So, ang gagawin natin dito is mag-aano talaga tayo, KVL, mano-mano. Okay, so this is a voltage divider bias na circuit or beta-independent circuit. But instead of an NPN, we have a PNP transistor. Now, familiar naman na tayo sa pag-solve nito, di ba? Ang ginagawa natin is tinetevenize natin yung circuit. Kino-convert natin itong 47 kilo saka 10 kilo na to into our RTH and then merong nakakonect na series na voltage, that is our VTH. So, familiar na tayo dun. But this time around, what we're going to do is the same assumption that we did earlier. Di ba? Ano yung assumption natin na yun? Instead of solving for IB, what we do is we solve for VB. Kasi parehas din. If we solve for VB, we can also solve for the rest of the parameters in the circuit. Ganun din naman, kapag sinolve natin yung IB, masusukat, mahanap din naman natin yung ibang parameters. But para maka-save tayo ng time or mapakita ko sa inyo yung another method sa pag-solve ng voltage divider, so, ganun yung gagawin natin. So, usually, ito tinuturo kasi itong dalawang method na to sa Electronics 1. So, kaso yun nga, hindi tayo nagka-time to or hindi nyo siya na-tackle in the previous na semester natin. So, for this, ganun din yung assumption. We will find VB and yung VB natin, that is approximately the voltage at your RB1 or R1. So, ganun yung papakita ko dito na solution na. Now, again, ano lang ba yung ano natin doon? Ano lang ba yung assumption natin kung bakit or ano yung condition na dapat nating masatisfy? That is kapag mas malaking yung value nung input resistance natin kaysa sa output resistance. Now, also, another one is kapag mas mataas yung value nung RE natin compare dito sa ano natin, sa R1 natin. So kung ganun yung case, if we can satisfy this equation, we can use the assumption that we did earlier. So kung ganun yung case, makita natin na satisfy. If yung beta RE mo daw mas malaki or equal sa 10 times ng R2, so that is 132 greater than 100 na satisfy natin. Then instead of mag-Theveninize, ang gawin na lang natin is mag-assume na lang na sobrang liit lang nung current na napupunta doon sa isang side ng circuit natin. So kung ganun yung case, yung VB natin, that is approximately equal to the voltage at this point. Sorry, hindi pala sa R1, sa R2. Kasi 'di ba, ang assumption natin, yung voltage mo at this point with respect to ground, that is also your voltage from this point papunta sa ground. So approximately, yung voltage mo dito is equal to the voltage mo sa VB. So if we get that, using simple na voltage divider rule lang, we have VCC times R2 over R1 plus R2. Then we will get a base voltage of negative 3.16 volts. So i-assume na natin that your voltage at this point is equal to this one. But in reality, hindi talaga. Kasi 'di ba, kung tutusin, this is your VTH, 'di ba? And kung yung VTH na yan, kakain pa ng kakain pa ng voltage yung RTH natin. Dun sa dati nating computation, 'di ba? So kakain pa ng voltage yung RTH. However, inassume natin na sobrang liit lang nung nagfo-flow na current doon sa ating base na kahit meron kang RTH, hindi na siya ganun ka-relevant kasi maliit lang naman yung current na dumadaan sa kanya. So kahit meron kang resistance at that point, since maliit lang yung current na dumadaan dyan, maliit pa rin yung kakainin niya na voltahe. So yun yung assumption na nangyari dito. So that's why, inassume na natin that VB is 3.16 volts. Pero ang totoo niyan, mababawasan siya talaga because of the RTH. Now, kung negative 3.16 volts yung VB natin, we can directly solve for VE. Kasi, alam natin yung value ng VBE. So, double subscript notation lang tayo. So, VE natin is equal to VB minus VBE. So, therefore, VE natin is negative 2.46 volts. So, one thing na gusto kong manotice nyo dito is that naka-negative or negative yung nakukuha natin na mga sign. Which is tama lang. Kasi, di ba, same process yung pag-compute natin, pero baliktad yung direction ng current. So, ibig sabihin, baliktad din yung sign na makukuha natin. Kasi negative or baliktad yung direction ng mga currents natin. Next, we have our VE. We can now solve for our IE. So, the current na IE natin is, if this is your VE, so maglo-loop ka lang din papunta sa ground. So, loop ka dyan and then papunta sa ground. So, this is your, kung ang direction ng current pataas, so ito yung positive, ito yung negative natin. Tapos, so kung ito, ayan, so pwede na tayong mag-loop ngayon. And kapag nag-loop tayo dyan, we will have an equal na value ng IE that is equal to VE over RE. Now, to be exact, negative to. Pero, ayun, again, the sign naman class, that is just the symbol of direction or nagpapakita lang siya ng direction. Kung ang maglo-loop tayo dito kasi sinimplify na, pero kung maglo-loop tayo dito, so kung positive to, kasi naglagay ka ng node dyan, and then, so negative dito, then we will have VE plus 1.1 kilo times IE is equal to 0 volts. So we will have IE is equal to negative VE over 1.1 kilo. So, and yung nakuha natin na VE kanina is actually negative. So kung negative yun, IE is equal to negative 2.46 volts over 1.1 kilo. So this is equal to 2.24 milliamperes, which is this one. So dito, sinimplify lang agad natin yung sign niya. But yun nga, again, the safest way talaga is mag-loop lang tayo na mag-loop. So for the collector to emitter loop, so VCE yung hinahanap. So mag-loop lang din tayo from this point papunta sa ground. We will have this equation, negative IE, RE. Tas, sir, bakit plus yung VCE? Kasi di ba naglalagay tayo ng reference. Pag naglagay tayo ng reference, malamang ang kinoconnect mo doon is the positive na terminal, not the negative terminal. So therefore, positive yung VCE natin. Kumbaga, itong kulay blue na to, tayo yung naglalagay niyan. Katulad nito, naglagay ako ng node na VE dito, reference, di ba? So, kung maglagay ng node dyan, ang assumption, syempre, yung positive ng multimeter mo, yun yung i-connect mo dyan. So, therefore, positive yung nakakonect dito. Kaya, ganun yung sign convention natin. So, ganun din dito. We take the output from the collector. If you take the output from the collector, the assumption is, the positive side, dun mo ilalagay. Kaya, ito yung positive na nakalagay dyan. Tapos, negative dito sa kabila. Kasi baka sabihin nyo, sir, di ba ang direction ng current pataas? So, dapat positive to, negative to. So, hindi ganun. Naglalagay tayo ng reference. Now, also, another thing na gusto kong tingnan nyo is, yun nga, kung this is a PNP transistor din, kumbaga. Ayaw mabura. Ayun. So, kumbaga, the sign lang talaga yung mag-iiba. So, this is our equation for the VCE. Assuming that our IE and IC is the same, so we will have an equation for VC na is equal to negative VCC plus ICRC plus IC times RC plus RE. And substitute natin yon, we will have a VCE that is negative 10.16 volts. Now, that is tama lang talaga. Kasi 'di ba, dito mo kinuha sa point na to. So, negative talaga yung makukuha mong value ng VCE kasi dito mo nilagay yung positive. Ang direction ng current mo pag ganito, papataas kumbaga in reference to this picture. So, kung gusto mo na positive yung makukuha mong value, yung V out mo dito mo kunin. Tapos with reference, dito yung ground mo. So, ganun class yung assumption lang natin. So, dapat alam nyo naman na yan, lang to circuits. Dapat napag-alalan nyo siya sa circuits 1 ba at sa circuits 2. Yun. So, that is how we solve for the characteristic ng isang PNP transistor. So, yun. Ganun lang siya. Similar lang talaga. Iba lang yung mga signs natin. Pero, kung paano mag-loop, paano magkuha ng mga values, similar lang. Now, at this point, I want you to pause the video and try to solve yung problem na to using without approximation. So, i-Thevenize natin siya. So, mag-Thevenins tayo. So, solve for the circuit. Ayan. So, ayan. Gawin nyo is using the same problem but different process. Instead of mag-assume tayo that your VB here is just the voltage at your 10 kilo ohm resistor, isolve nyo siya using Thevenin circuit. So that means ite-Thevenize nyo siya, i-consider nyo yung RTH natin. Hindi katulad kanina, hindi na natin siya kinonsider. Yan. Yeah. Next, the last topic for this chapter is yun nga, transistor switching networks. So kapag transistor switching networks naman, what we will be talking here specifically is the other function of a transistor, and that is as a switch. Kumbaga, we have discussed heavily paano siya nag-work as an amplifier. But this time around, as a transistor, switch naman siya. So, actually ito, tinidiscuss ko to Electronics 1. Pati yung buong chapter na to is Electronics 1 ko talaga siya dinidiscuss. However, yun nga, since hindi naman tayo umabot, tapos sinama kasi ito sa syllabus ng Electronics 2, sakto na rin. Kasi since hindi nyo naman siya na-discuss last sem, okay na rin na i-discuss natin. But yun lang, kasi baka magulat kayo na bakit ngayon lang natin ito pinag-aralan. Kasi supposedly, pinag-aralan nyo na to last sem. Sinama siya sa curriculum nung gumawa nung syllabus. So, di ko na talaga siya i-discuss. However, since di naman siya inabutan, sakto lang din. So, i-discuss na rin natin siya. Ayan. So, transistor switching networks tayo. Analyze muna natin tong circuit na to. We have an input voltage daw. Dito natin siya pinapasok. And then, we have an output na dito natin kinukuha, VC. Tapos, yung input natin is a square wave. Yung output natin is also a square wave. Now, analyze natin paano kaya nag-work tong circuit na to. At this point, nung circuit natin, yung input natin is 0 volts. So, ibig sabihin, walang voltage na nagpapass dito sa RB natin. Kung wala nagpapass na voltage dyan, then ibig sabihin, wala ring current na nagpo-flow or dito sa circuit natin. Remember, ang transistor natin, it can work as a switch. Meaning, kapag meron kang enough current na pinadaloy dito, this side will be shorted. Magkakaroon ka ng current flow. Now, assuming na wala kang current na nagpo-flow dyan, then therefore, wala kang open to, kumbaga. So, therefore, open to. And kapag open yan, ano yung value ng VC natin? Now, the value of VC natin kapag open yan, so syempre, kung magluloop ka from this point, magluloop ka papunta dito. So, kapag nagloop ka papunta dyan sa labas, you will have VCC times VCC minus ICRC is equal to VC. Now, assuming na mababa lang, kumbaga tanggalin muna natin itong assume natin na mababa lang yung value ng ICRC natin. Magkakaroon ka ng output na, or kumbaga, kunin natin to with respect to ground. Kasi yung ginawa ko na circuit na to, parang it's as if hinati natin yung voltage. But, ang assumption natin, the voltage at this point, which is VC, is equal to the voltage at this point din. Kumbaga, itong buong branch na to, ano yung voltage dito from the VCC to RC, kunin natin yung voltage niya as VCC with respect to ground nito. So, kumbaga, i-redraw yung circuit So, we have RC to, RC, VCC. Kumbaga, imagine niyo lang class, naglagay ako ng voltmeter dito. That is, yun yung RC. And kapag naglagay ako ng voltmeter dyan, then therefore, the total voltage na makukuha ko dito is voltage nitong dalawa. And yung voltage ng dalawa na yan, syempre, dito lang magagaling sa VCC. So, kung ganun yung case, yung VC mo will be equal to VCC. So, therefore, at the time at which ang input voltage mo ay 0 volts, lahat ng voltage mo dito manggagaling. So, we will have a value na equal sa VCC, which is 5 volts. Now, let's say, for example, mapunta ako sa part na to ng circuit. Sa part na to ng square wave natin, rather, not circuit, yung input natin is already 5 volts. Now, kung 5 volts yan, magkakaroon na ng current dito. Now, assuming na yung 5 volts na yan is enough para i-on tong circuit, meaning ang mangyayari is mag-short to. Okay, take note as a switch yung pinag-uusapan natin. Kapag as an amplifier, may voltage drop tayo dito na VCE. But if switch yung pinag-uusapan natin, sabihin enough yung voltage mo para makapag-work at the saturation region. Enough yung voltage mo para makapag-work at the saturation region. Magpo-flow lang current dito. 0 yung voltage natin dyan. So kapag 0 yung volts natin yan, shorted yan. So kung shorted yan, at this point, ano yung makukuha mo na voltage? So, siyempre, ang dadaan ng kuryente mo, or hindi ka na kukuha ng voltage at a point na may resistance, di ba? So, pwede kang mag-loop dito na lang. So, from VCC, papunta sa ground. So, maglo-loop tayo dyan, we will have, VC lang pala, we will have VC is equal to 0. Kasi, to be exact, VC minus VCE is equal to 0 volts. But assuming na yung VCE natin is equal to 0 volts, we will have VC is equal to 0. So therefore, kapag may input na current dito, ang output mo is 0 volts. And then, hanggang dito, bababa na naman sa 0. So pag bumaba sa 0 yan, open na naman tong part na tong circuit. At kapag open na naman yung part na yun ng circuit, dito ka ulit kukuha ng voltage and equal na naman yun sa 5 volts. So that is how the transistor works as a switch. So, actually, na-discuss na ko na to dun sa example na circuit natin kung paano nag-work nga yung mga transistor. Now, ang tanong, paano siya dinedesign? So, yun yung pag-aralin talaga natin dito. So, kumbaga, introduction lang tong pinakita ko dito sa figure natin. But ang pag-aaralan talaga natin is, ano yung mga conditions para masabi mo that your transistor will work as a switch. So, babalikan lang natin yung discussion natin with BJT. Now, ito yung circuit natin kanina. Now, ano ba to? Yung nasa right side natin, this is the characteristic curve. Tapos, may naka-superimpose tayong load line. Now, balikan muna natin, ano ba yung characteristic curve? This is, to be specific, the output characteristic curve of a transistor. This is a graph of the output voltage to the input current, output current at different values of your input current. So this is a graph of your V out and your I out at different values of I in. So to be exact ang pansinin nyo lang muna yung kulay blue. Huwag nyo tingnan yung kulay black. Kasi yung kulay black, load line yan. Ang characteristic curve, yung kulay blue. So ano ba yung dinedescribe yan? O ganito lang yan. Halimbawa, kung ang input voltage input current mo ay 10 microamperes. Ito yung relationship, itong curve na to describes the relationship of your V out and your I out. So to be specific, common emitter na ano to, na common emitter na configuration. So kung common emitter siya, yung V out mo is VCE. O ito pala, VCE. At ang I out mo is IC. Tapos ang input current mo is IB. So ganun yan, 'di ba, kapag common emitter yung pinag-uusapan natin. Now, at an input na 10 microamperes, this is the relationship of your V out and your VCE and your IC. So ibig sabihin, halimbawa ang value ng V out mo ay around 2 na volts. Then therefore, yung I current mo, yung I out mo will be approximately, sabihin natin, nasa 1.3 milliampere siya. So ganun natin ginagamit tong configuration characteristic curve. So it is the different relations of your output parameters based from your input. So kung halimbawa 60 ang IB mo is 60 microamperes, then ito naman yung characteristic niya. 'Di ba? So kung ang voltage mo ay 2 volts, ang output current mo is nasa ganitong value. Sabihin natin mga nasa 7.3, ganun. So ganun natin to, ganun yung natin dito pag-analyze. Now ang tanong, paano nga ba natin siya ginagamit? So 'di ba, ginagamit natin to load line analysis. So pag load line analysis, based naman yun dun sa circuit. So hindi ko na maalala kasi to what extent yung na-review natin. But ang kailangan nyo lang naman maintindihan is that yung output, yung characteristic curve natin, based yan sa transistor. Yung color blue, characteristic yan ng transistor. So, given na yan. Nasa specification sheet, mga ganung bagay. Now, ano yung naiiba natin? Ang naiiba natin is the load line. Yung kulay black na line. Yung load line na yan, class, nakabase yan sa circuit mo mismo. If the characteristic curve is based on your transistor, your load line is based on your circuit. And in this case, this circuit, ito yung load line niya. So, paano natin na-compute or paano natin na-draw yung load line na yan? Simple lang naman. To draw the load line, we use the circuit. And para makapag-draw ka ng line, di ba ang kailangan lang naman natin is 2 points. So, we only need 2 points. So, to get those 2 points, we can just use a value kung saan, di ba, VCE tsaka IC yung value natin. So, ang gawin na lang natin, we need 2 points. So, hanapin natin yung value ng VCE when IC is equal to 0. And hanapin natin yung value ng VCE ay IC when VCE is equal to 0. So, itong dalawang points na to, yun yung pa-plot natin. Tapos, pagko-connect lang natin sila. So, to find the working equation, kailangan natin ng nag-relate dito sa dalawang to. Diba? Napakadali. Ang nag-relate sa dalawang yan is just the equation pag nag-loop tayo dito. Actually, tama, hindi pala dyan. diretso sa ground kasi kailangan natin ng VCE. So, pag nag-loop tayo, pababa dito. So, we will have VCC, tapos ICRC to. So, therefore, may IC yan. Tapos, VCE. So, therefore, meron din siyang VCE. So, we already have an equation relating the two. So, we will have VCC minus ICRC minus VCE is equal to 0. So, ang equation natin is VCC minus VCE is equal to ICRC. VCC is constant, RC is also constant. So, using this example, try nating i-draw yung load line. Start tayo, assume natin that VC is equal to 0 volts to get IC. So, we will have IC is equal to 6.1 milliampere. So, therefore, 1 point at our load line is 0 volts, 6.1 milliamperes. Next, at IC naman is equal to 0 amperes. We will have 5 minus VCE is equal to 0 amperes times RC. We will have VC is equal to 5. So, therefore, meron din tayong point sa load line natin na 5 volts, 0. 0 amperes. So, may dalawang point na tayo. I-plot na natin siya sa circuit. That is, at VCE is equal to 0, your I is 6.1 milliamperes. And that is, at I is equal to 0, your VCE is equal to 5 volts. Then, kinonect lang natin sila. You already have your load line. Now, remember class, we have different regions of operation in a transistor. Diba? So, to be exact, itong portion na to, sorry, ang pangit ng paggawa ko. This is what we call as the saturation region. Now, we also have this portion na nasa baba. Ang tawag natin dyan is the cut-off. Cut-off region. And then yung area naman na to, ang tawag natin dyan is the linear or active region. Now, ano ba yung naalala about dyan? So, kapag ang Q point mo or ang quiescent point mo ay nasa active region, mag-work siya as an amplifier. Kapag ang Q point mo ay nasa saturation region, mag-work siya as a switch. At kapag nasa cut-off region, ang Q point mo, mag-work siya as wala, naka-off yung transistor natin. So, ganun class yung regions of operation natin. So, yun, kailangan talaga reviewin na lang, no? Kung hindi na familiar, reviewin na lang. Or mag-request kayo sa akin ng discussion na lang. Pero alam ko na-discuss ko to nung review session. So, yun. So, yun yung tatlong region of operation natin. So, kadalasan class, dun sa mga discussion natin, ang output natin ay, since ang discussion natin, puro amplifier, andito tayo sa area na to. Hindi ko alam, mabuburara ako kasi. Nasa linear region tayo. Diba? Kaya nga, pagka nagko-compute tayo, diba, ano yung value ng VCE natin? Diba usually mataas? And kung titingnan natin dito, at the active region, yung VCE mo may value. VCE mo, halimbawa, x-axis, diba? That is around, meron kang value na 1 volts to 2 volts, etc. Pataas ng pataas yung value. So, ganun class yung computation natin. Because most of the time, we compute at the active region. But remember earlier, what we did is we assume that our VCE is equal to 0. Now, if that is the case, nasaan ba dyan sa portion itong circuit natin or nitong graph natin rather, na ang output natin is, yung VCE natin is nasa 0. Di ba nandito sa left side? So, nandito sa side na to. So, this is your saturation region. This is the point at which nag-work yung circuit mo as a switch. To be exact, as an on na switch or naka-close yung V to CE mo. Kasi 'di ba, kapag ang VCE mo ay 0, kapag ang VCE mo ay 0 volts, meaning shorted 'yan. At kapag shorted 'yan, wala siyang voltage drop. So wala siyang voltage drop, then magfo-flow lang current directly. So para talaga siyang literal na switch. So, ganun siya nagpo-work. Now, ito na ngayon yung kung bakit natin sila pinagpapatong. Di ba kaya natin sila pinagpapatong? Para malaman natin ano ba yung magiging region of operation niya. Tapos kung mag-work ba siya sa intended na operation mo. Itong load line na to, class, and the intersection of your load line to your characteristic curve, that is your quiescent point. So assuming na ang input voltage mo ay 10 microamperes. Kung 10 microamperes yung input voltage mo, then therefore, this is your Q point. Let's say Q sub 1. O Q point sub 1 na lang para hindi malito. So this is your Q point sub 1. Kung Q point sub 1 ang input current mo, ano mangyayari? Will it work as a switch or as a amplifier? This will work as an amplifier. Diba? So ibig sabihin, dapat yung sa circuit natin na to, kung gusto mo siyang mag-work as an amplifier, hindi pwede na yung input mo is just 10 microamperes. So hindi to pwede. So tingnan pa natin, ano dapat yung value mo ng input? Kapag 20 microamperes, hindi pa rin pwede. Kapag 30 microamperes, hindi pa din. Kapag 40, hindi pa din. So pwede na kapag 50. Bakit? Kasi kapag 50 microamperes, approximately is nandito ka sa saturation region. So ibig sabihin, approximately 0 volts yung voltage drop mo sa VCE. And kung 0 volts yan, wala siyang, hindi siya kakain ng voltahe. And mag-work siya as a closed na switch. So yun yung gusto nating mangyari, na nag-work tayo at this region. So alam mo na rin na yung maximum na voltage mo or na current mo is dapat magpo-fall dito. So pwede na, sige, around 50 microamperes pasok, about 60 microamperes pasok. Pero at 40 microamperes, wala na, lagpas na kasi ang Q point mo nandito na. So therefore, hindi na siya mag-work as a switch. Mag-work na siya as an amplifier. Now, kapag naman nakapatay yung switch natin, gusto natin naka-open siya, di ba? So, kung gusto natin naka-open siya, that is approximately at a value of, wala ka dapat current na magfo-flow, di ba? Kung wala kang current na magfo-flow, then dapat sobrang mababa yung kailangan na value mo ng IB. Kasi para hindi mag-flow yung current, dapat nasa cut-off region ka. And para makarating ka sa cut-off region, kailangan yung input current IB mo is approximately 0 microamperes. Kasi kapag 0 microamperes ang input value mo, ayan nakadikit ka halos sa x-axis. So therefore, wala kang value ng y. So ganoon naman yung gusto nating mangyari kapag naka-cut off region tayo. So ito, class, yung visual representation on how we get or determine kung pumapasok ba tayo doon sa region na gusto natin. Kung saturation ba siya, linear ba siya, or cut off. Now, tingnan natin siya in terms of computation naman. So when the current is saturated, then VCE is equal to 0 volts. That's our assumption. For this part, ang gagawin natin lang, class, is gagawa tayo ng paraan na ma-determine kung enough ba yung mga yung mga parameters, paano ba natin siya makukuha in terms of computation naman. So, siyempre, ang assumption natin, switch tayo. So, 0 volts natin yung VCE. So, at saturation, then meaning your current mo at the saturation, loop ka dito, is just VCC over RC kasi wala na nga to, di ba? 0 volts yan. HFE, class, that's just beta DC. So, different lang each parameters, pero same lang siya with beta. So, kung walang VCC, nag-loop ka dyan, IC sat mo or the saturation current will just be VCC over RC. Now, the level of IB in the active region just before saturation occurs can be approximated by this equation. So, kumbaga, ang gagawin natin, from the active region, yung point na to, let's try to find the IB at this point. Yan, yung bago siya lumipat sa saturation, kunin natin yung IB niya. And paano natin siya makukuha? And then that is just the relation of your saturation current with regards to your beta or ratio lang nila. So therefore, yung maximum na value ng IB mo, bago niya ma-reach yung saturation region, is just IC sat over beta DC. So for the saturation level, we must therefore ensure that the following conditions is satisfied. We need to have an IB max or IB natin should be bigger than IC SAT over BDC. Kasi alam niyo yung mangyayari, class? Kapag yung IB natin is mas maliit compared sa IC SAT over beta, magfo-fall yung region of operation natin dito ng bahagya. So, dyan siya kumbaga. So, hindi siya magfo-fall doon sa saturation region. So, therefore, dapat yung value ng IB natin is mas mataas kaysa sa value nung maximum kumbaga. Kailangan mas mataas siya dito. IB max is the maximum base current for the active region. And kapag sumobra ka sa IB max, nasa saturation region ka na. So therefore, kailangan mas mataas ka dito kasi ang gusto mo nga mag-work ka at the saturation region, di ba? So therefore, IC SAT over beta, dapat mas malaki yung IB mo doon. So for this network, so di ba kanina, ang input natin is 5 volts. If input natin is 5 volts, we can solve for IB. So maglo-loop lang tayo dito. Input natin dyan, 5 volts, mag-loop lang tayo dito. So VB ito. So we will have an equation for IB na VI minus 0.7 or VBE over RB. And that is 5 volts minus 0.7 volts over 68 kiloohms is equal to 63 microamperes. So, ibig sabihin, class, ito yung actual na input voltage dito. This is your actual beta. Now, dapat, itong actual beta na to, mas malaki to kesa sa IB max natin. So, yun yung gusto nating mangyari. Compared dito sa IC SAT over BDC, kailangan mas malaki yung beta, which is, nakuha natin 63 microamperes. So, therefore, we have to solve for IB. Eh, na-solve naman natin yung IC SAT kanina kasi yan yung ginamit natin for the load line, di ba? So that is approximately 6.1 milliamperes. Iyan yung ginamit natin pang solve ng output current sa load line. Pero kung gusto niyo ulit is-solve, napakadali lang. Since saturation, ang assumption mo, this is 0 volts, loop ka dyan. We will have 6.1 milliamperes. Now, testing the equation, hanapin muna natin yung IB max natin. That's 6.1 milliamperes over beta. That's 1.25. That is equal to 48.8 microamperes. Now, mas malaki ba yung 63 microamperes kesa sa 48 microamperes? Yes. So, therefore, IB is greater than IC SAT over beta DC or beta. So, therefore, nag-work siya as, mag-work tong circuit natin as a switch. Ayan. So, ganito yung natin, assumption na ginagawa. Tapos tingnan natin in terms of the resistance. Kanina kasi sinasabi lang natin walang voltage drop ganyan. Now, tingnan natin kung paano siya kapag titingnan natin siya in terms of the resistance. Now, assuming muna tayo closed yung switch. So, meaning, meron nagfo-flow na current dito. Kung ganun yung case, then therefore, kung merong ini-introduce na resistance tong area na to, let's say that's your RSAT, and meron kang current dyan, tapos meron ka supposedly voltage drop dyan na VE-SAT. Now, ang assumption natin, VCE-SAT is equal to 0 volts. But in reality, yung VCE-SAT natin class, nagbibigay ng value na around 0.15 volts. So, sobrang baba lang. So, assuming na hindi tayo mag-approximate that VCE-SAT is equal to 0 volts, ang gawin natin, lagay natin yung typical na average value niya, which is 0.15 volts. So, using the same circuit, we will have, via Ohm's law lang to, 0.15 volts over 6.1 milliamperes. Ang sagot natin is 24.6 ohms. So, this is already a very low na value ng resistance. And for most applications, this be considered as 0 ohms na. Compared to ang RC mo, nasa kiloohms, kumbaga. Tapos, iyan, nasa 20s lang. So, negligible na siya. Kung magkakaroon man yan ng voltage drop, sobrang iksi lang or sobrang maliit lang yung magiging voltage drop niya. So, therefore, 0 na to. So, kung 0 na yan, para na siyang nag-act as a switch na close, na shorted na yung circuit natin. Now, kapag ka naman nasa voltage na tayo, ang input voltage natin ay 0 volts. So, ibig sabihin, kung 0 volts yan, yung input mo dito, magkakaroon ba tayo ng IB? magkakaroon ba tayo ng IB na mag-flow dito? Di ba wala? Kasi wala ka namang input voltage. And nakita natin sa figure natin, when your IB is equal to 0 volts, ito siya. Your IC is, kahit gaano ka tumaas yung VCE mo, yung IE mo is just, IC mo pala rather is just 0 volts. So, ganun din dito. So, kung ito ay walang nagfo-flow na current, then the assumption is open naman to. Now, kung titingnan natin, let's say, i-equate natin siya to a resistance. Assumption natin is totally wala talagang current na nagfo-flow. Kung wala nag-current na flow, bio ohms law lang din. Instead of RSAT, this is the resistance at the cutoff region. Kasi nakita naman natin sa characteristic curve kanina, di ba? Nasa pinakababa siya. So, using Ohm's law, that's VCE over IC EO, meaning, collector voltage kapag naka-open yung emitter ay collector to emitter junction mo, open siya. So kung open yan, it is 0 milliamperes yan. And 5 volts VCC mo divided by 0, that is infinity. Ayan, but however, kung katulad nito kanina, hindi naman talaga totoo na open yan. May nagpo-flow pa rin na current, pero sobrang liit lang. Now, for a typical na circuit, ang ICEO mo, usually nakikita rin to sa mga specification sheet, is nasa 10 milliamperes. So, gamitin natin yung value na yan. Kung 10 milliamperes, mag-ohms na tayo ulit. Yung cut-off, yung resistance at this junction, C2E junction natin, at cut-off, that is 5 volts over 10 milliamperes. And that is equal to 500 kilo ohms. So, ito naman, mataas naman na yung value niyan. And yung ganyang value is, pwede na siyang i-consider for many situations as an open circuit equivalent. So, ganun class yung nangyayari. Ayun, so ganun lang tayo mag-analyze ng mga transistor circuit as switches. So, example tayo. Determine RB and RC daw for the transistor inverter if IC SAT is equal to 10 milliamperes. So, pinapanap sa atin is RB tsaka RC. Now, for this kind of question, hindi talaga to ginagawa for like theoretical na exact na value, ganyan. Kasi most likely dito, class, halimbawa, imagine niyo yung sarili nyo. Magde-design kayo ng circuit. Pag magde-design kayo ng circuit, syempre, pipili kayo sa market ng resistor, di ba? And ang gagamitin yung resistances kung ano yung available doon sa market. So for this one, talagang parang design siya na kayo yung bahala humanap ng range ng RC tsaka ng RB na pwede nyo siyang gamitin. So pwede na may mga tayo dito na makukuha talaga based from computation, but meron ding part na mag-a-assume lang tayo or magta-try tayo ng mga value. So try natin siya. So at saturation, IC SAT is equal to VCC over RC. So in this case, madali nating ma-solve yung value ng RC. Kasi given yung IC SAT, nasa circuit yung VCC. So therefore, RC natin is just equal to 1 kilo. So, and 1 kilo is available in the market. So, meron kayo niyang mabibili na manufactured na ang resistance niya is 1 kilo. Now, next is IB. To solve for RB naman. Now, at saturation, let's try to solve muna for IB. We have IC SAT over BDC, beta is equal to 10 milliamperes over 250. Again, yung HFE, that's also your beta, is equal to 40 microamperes. So, ano ibig sabihin nito, class? Dapat, kung ano yung bibilin mong value ng RB, yung kakalabasan na sa circuit mo, dapat mas malaki to kesa doon sa kumbaga, mas malaki to kesa sa IC SAT over beta. Nung mismo actual na circuit natin, So, let's say for example, to ensure na saturation, ang gusto mong value ng IB mataas na. Let's say 60 microamperes na. Now, kung ganun yung case, yun yung sa-substitute natin dito. Hindi pala. Mali akong sinabi. So, hindi yan yung isa-substitute natin. Ang gusto nating mangyari, class, is pumasok tayo na mas malaki dito para safe. kumbaga. So, ibig sabihin, kung ano yung value ng RB na ilalagay natin dito, dapat masatisfy niya yung condition na binigay natin kanina. So, let's say for example, ang value ng RB na ilagay natin is 150 kilohms. So, take note at this point, kumbaga, we let RB be equal to 150 kilohms. So, ganun class yung ginawa natin. Tayo nag-assume ng value for RB. Now, yung value ba yun ng RB is enough? Or tama ba yung value na yan para masatisfy yung mga conditions natin? So, to do that, we substitute. So, pinalitan natin yung RB dun sa circuit ng 150. Nag-loop tayo, we will arrive at this equation. And ang output natin, or ang nakuha natin na value is IB is equal to 62 microampere. So, para hindi malito, ito yung IB max. Ayan. But instead of using 40 microamperes, para safe, ang ginawa natin, yung IB max na gagamitin natin is 60 microamperes. So, therefore, yung IB natin na nakuha, which is 62, is mas malaki kaysa dito sa 40 microamperes. Ayan. So, mali pala. Kumbaga, sabi na kulang tong kulang tong equation. So, bali ganito, using 60 microamperes, yun yung ginamit natin to find the value of RB. Tapos nakuha tayo ng value ng RB, however, may butal yung nakuha natin. So, dahil may butal yung nakuha nating value ng RB, naghanap tayo ng value ng RB na available sa market, which is 150 kilohms. So, yan. So, sorry pakita ko na rin. So, instead of using 40, gusto natin mataas, ang inassume natin is 60 to. So, mali to. Hindi talaga to max. Sorry. Ayan. So, nilagay natin dito yung 60 microampere. So, therefore, yung RB natin na makukuha dyan is, so, 10 volts minus 0.7 divided by IB natin is 60 exponent negative 6 divided. So, 10 minus 0.7 divided by 60 exponent negative 6. So, ang nakuha natin is 155 kilohms. However, walang available na 155 kilohms doon sa market, kumbaga. Walang industry made na 1.55 kilohms. So, therefore, gamit tayo ng iba. So, ang ginamit natin is 150 kasi yan, available yan. Now, kung 150, syempre, itetest pa natin kung pwede talaga siya. Now, kung pwede siya, para malaman natin kung pwede siya, i-substitute natin siya dito sa equation natin na to. And nakuha natin is 62 microamperes, which is still greater than IB max natin na 40 microampere. So, therefore, we can use RB as 150 and RC at 1K. So, ganito yung gagawin niya lang, class. Solve muna yung RC. Pag na-solve nyo yung RC, tapos yung value ng RC na nakuha nyo available in the market, then agad-agad yun na yung answer nyo. Like in this case, sa problem na to. Since yung RC natin, 1K yung nakuha niya and merong 1 kilo sa market, then yun na yung gamitin natin. Kasi design na tayo eh. For this problem kasi kinoconsider na natin design. So meaning, kung gagawin mo yung actual circuit, dapat available yung ganyang resistance sa market. Next, solve for RB using this equation. Kapag yung nakuha mong RB is exact din siya na merong available sa market, then yun na yung gamitin mo. However, kung hindi, hahanap ka ng malapit dun sa value na yun. And in this case, yung pinakamalapit is 150K. Now, para masigurado mo na magagamit mo talaga siya or papasok pa rin siya sa criteria, i-substitute mo siya dito sa equation. So, ganun din dito sa RC. Kung hindi exact yung nakuha mo, let's say ang nakuha mo is 1.07 kilohms. So, kung wala yan sa market, pili ka ng pinakamalapit. Let's say ang pinakamalapit na nakuha mo is yun din, 1 kilo. Then, substitute mo siya dito. At kapag sinubstitute mo siya at pumasok yung value niya, then therefore, pwede mo siyang gamitin. So, ganun class yung ano natin dito, assumption. Ayan. So, next is switching transistor. So, for this part, wala tayo talagang masyadong problem solving. Actually, pati yung problem solving natin kanina, more on para lang makita kung paano ba siya nag-work. So, kasi ang concern natin talaga dito is just more on the design. Now, in this part, very simple lang din yung computation natin dito. Gusto ko lang ipakilala sa inyo yung mga switching transistors natin. So, meron kasi talagang tayong mga transistor na ang purpose niya talaga is for switching. And the reason is, mabilis yung pag-switch nila from active region, from cut-off, punta ng saturation region, mabilis siya mag-on, mabilis siya mag-off. So, yun yung gusto nating mga transistor for switching. So, to be specific, meron tayong tinatawag na T-on or the time at which nag-on yung circuit natin, and T-off or the time at which bumababa yung circuit natin. Now, to be exact class, T-on is the time at which yung circuit natin is tumataas yung value niya to 90% of the IC. So, this is a graph class of time versus current. Ito yung reaction, kumbaga, or behavior of our transistor, yung kulay blue na to. Ayan. And from an off na state, let's say off yung state mo, tapos biglang nag-on siya. That is your T-on. Pero yung T-on mo, that is the time at which from 0, ma-reach niya yung 90% of its on current, of its saturation current. So like this one. So from 0, ma-reach mo yung 90% ng current mo, that is the time at which masasabi mo na on yung circuit mo. And the time it takes para ma-reach mo yung 0 to 90%, that is what we call as T-on. Now, ano naman yung time na nag-off ka? Yung T-off naman, class, this is the time at which na ma-reach mo from the value of 100% is ma-reach mo yung 0. So, that is the time naman at which nag-off yung circuit mo. So, kung makikita nyo dito sa figure natin, madali nang ma-figure out kung ano yung formula for T-on tsaka T-off. Kasi ayan, parang sum lang siya ng TD tsaka ng TR, T-on yun. Tapos sum ng TS tsaka TF, that is T-off. Well, actually, true yun. So, the total time required for the transistor to switch from the off to on state is designated as T-on and is defined as TR plus TD, which is very obvious naman dito. TD tsaka TR. TD is known as the delay time. This is the time at which from 0, makareach ka ng 10%. And yung TR naman, that's the rise time. That is the time at which from 10%, ma-reach mo yung 90%. Ang T-on from 0 to 90. O de, add mo lang yung dalawa. So, we have TR plus TD. Next, the total time naman for a transistor to switch from the on to the off state is referred to as T-off and is defined as TS plus TF. Wherein TS is the storage time. So, kumbaga, TS is wala nang voltage, wala nang ano dyan, wala ka nang input. Pero, meron ka pang, may ano ka pa, may, anong tawag dito? May naiwan ka pang voltage. Yun yung storage time. So, gaano katagal maiwan yung voltage doon? Yun yung TS. And then, yung TF naman is, that is the time at which magfo-fall yung output current mo from 90% to 10% of its initial value. So, add mo lang. So, madali lang siya talaga. So, ito. Example daw. So, find T-on and T-off for the specification sheet of a general purpose transistor shown in the figure at IC is equal to 10 milliamperes. So, pinapahanap yung ano natin, yung T-on saka yung T-off natin. So, to do that, ito lang. Sundan lang natin yung graph natin. By the way, itong figure na to, class, this is an actual specification sheet. So, iyan na iyan mismo yung ano natin, kumbaga. Iyan na iyan yung ginagamit or ganyan yung pinapakita sa mga ano natin, sa mga pagka bumili ka, tapos nanghingi ka ng specification sheet, so ganito yung itsura niya. So, paano natin gagamitin yan? So, given that IC is equal to 10 milliamperes, hanapin lang natin asan yung 10 milliamperes dito. So, yung 10 milliamperes natin, ito siya. So, kunin lang natin yung current at this, ay yung time at this point, at this point, at this point, at this point. Yun na yung values nung TS, TD, TR, tsaka TF natin. So, at 10 milliamperes, your TF is approximately mga nasa 12 nanoseconds, ganun. So, yun lang gagawin natin. Now, based from the figure, we can find that approximately TS is 120. Ito yung TS. So, kung 10 milliampere, ayan, tingnan natin kung tatama yung hula natin. So, at 10 milliamperes, ito yon. Grabe, in-effortan ko maging tuwid pero ayaw talaga. So, ito yon. So, sabihin natin nga na that's approximately 120 nanoseconds. TD, so ito siya sa point na to. So, mga nasa 20 something. Mga 24, ganun. TR is this one. So, mga nasa around, mga nasa 15 to 16 nanoseconds. TF natin is mga nasa 12, ganun. So, hula-hula lang natin yan. Approximation lang based from the graph. So, assumption natin, TS, nasa 120 nanoseconds. TD, 25. Okay na lang yung hula natin kanina. Ito rin, okay din hula natin. 13 nanoseconds. And TF is nasa 12 nanoseconds. Now, we can now solve for T on tsaka T off. So, for T on, that is TR plus TD is equal to TR natin is 30 nanoseconds. TD is 25. So, therefore, we have 38 nanoseconds. And T off natin is just TF plus TS. TS natin is 120. TF natin is 12. So, ang turn off time natin is 132 nanoseconds. So, yun. Ganun lang yung natin, pagsosolve. So, importante lang na sanay tayong magbasa ng mga specification sheet. And so, that is it for the discussion natin for this chapter. So, kung may question, please do ask me in Messenger or in Google Classroom. Ayan. So, thank you so much.